my name is Juan. As the chair introduced me, I'm doing PhD at ANL. I'm here to talk a little about the work I've been doing, called Extreme Learning Machines in Artificial Sensory Oscillator Neurons. This is a common slide for everyone here. It was from a past presentation, but here in our project, we are inspired by the human brain. It consumes low power, and the neurons in the brain communicate through synapses that also cost around 1 femtojoule to communicate, and they allow for event-driven sensing and on-edge processing, low energy preparation, and massive parallelism. And our idea is to explore how to replicate this on chip. For that, we are working with resonant tunneling diodes, especially aluminum gallium arsenide RTDs. These structures employ a double quantum well barrier. And how this works: when we submit the device to a certain voltage, the electrons will tunnel through the barriers, and the current will occur. As we increase the voltage applied, the energy on the emitter side will start to increase until a point where the energy on the collector is higher than the permitted energy on the collector to the tunneling to occur. So we'll reach a peak level current. After that, no more tunneling will happen, and the decreasing current will be seen. And after increasing a lot the bias, the tunneling will start again. So in this way, we create a negative differential resistance region that will give a gain to the overall setup, and we can see this as oscillations when we bias inside this point. So how do we fabricate this kind of devices? First, we start from our gallium arsenide wafers. We use direct light laser for pattern the masks. We etch we do the mask for the pillars. Then we use ion coupled plasma to etch these structures. We do the same process, but to isolate devices from pillars from each other electrically. Then we passivate with silicon oxide, and we open a certain bias on this silicon oxide, so we can metallize, but also to create some openings. I forgot to mention, but these layers, we also have photosensitive layers, so we can emit light and it will detect. This is the kind of structures we build now. We build pillars from 6 to 10 microns, really small. For metallization, we use germanium nickel gold for both contacts, so there is the lowest resistance we saw. And these are the different configurations. First, single devices where we explore the basics, such as the oscillations, and we try to extract the NDR, so on. Then we want to see how these devices can communicate between each other, so we connect them through the top contact signal. And then in a more complicated case, and to allow for a network study, we have this 5x5 array of devices. So experimentally, how we characterize these devices. This is the setup. We inject 830 nanometers laser light on top of the device, and we sweep the bias with a DC power source. In this case, in our devices, a funny thing happened. That is, in dark conditions, no NDR appeared, but when we start to illuminate the device with more and more power, we start to create the NDR, and it will get more pronounced. This is due to the fact that when we illuminate the devices, electron-hole pairs are originated in the barrier, and this increase the energy, and we can get this NDR. And when we bias in the beginning or the end of the NDR, we get low amplitude and frequency oscillations, and as we go more inside the device, the region, this oscillation starts to get higher in amplitude. And so we try to explore giving pulse modulated light. We can, for that, we bias the device inside the NDR, and so it's always oscillating. By tuning the amplitude and the frequency of the pulse, we can pass from constant oscillations to a burst type spiking behavior, and this only consumes the consumption of this is around 230 femtojoules per pulse. Also, we explore the photo detection of these devices. For that, we give a 2 megahertz pulse and we square pulse, and we extract the voltage output of the device, and it works more or less as a common photo detector device. It's still slow in detection compared to the normal ones. We have rise and fall times of around 3 to 5 nanoseconds. Nonetheless, and based on the talk in the morning about leak integrated neurons, we also give a pulse strength to the device, 1 pulse, 2 pulse, up until 4 pulse, and we can these pulses are 1 nanosecond, and we can see that we get this graded response from the devices that we can use in the future to compute, to do computation. This response depends not only on the power of the light we are giving to the device, but also the region we are biasing. Focusing on the electrical part, we explore the oscillations. The device, when biased inside the NDR, can achieve between 60 to 50 megahertz, 60 kilohertz up to 50 megahertz. This is because the configurations we try involve cables, and by using more cables or different cables, the inductance and the capacitance of the system change, and the device is just giving a gain to the noise in form of the oscillations. And electrically, by giving a RF pulse, we can also achieve the same bursting. So with this in mind, we try to explore a simple problem, like talk in the morning. We approach stream learning machines, how this works. The device is our hidden layer. We just use one RTD, since we don't have the setup to bias a lot of RTDs at the same time. The stream learning machines, we give the data to the device, we collect the voltage response at the output, and then we just train a simple matrix inversion to make the classification. So for this case, the data is encoded as voltage pulses. We still didn't try it optically. We encode two voltage levels between the device being off at 0 volts or inside the NDR. Then we collect the bursting response. We sample the data and train the model. We also simulate using this setup that is the equivalent to the RTDs. So we tried simple tasks such as regression, just simulation because it's too simple. We were able to basically reconstruct this function. Then we compared the performance of our system to linearly training the model with the raw data. We can see we can get basically 99% accuracy in simulation, besides the mostly square Bandio arrays. This is caused because in the simulation we didn't consider noise drift that can occur during the experiments, but experimentally we get a better division between the two classes of the spiral, and it proved that we can use it. Finally, we tried also the MNIST dataset. For that, we binarized the image between 0 and 1, and then we encoded as voltage bias again. We compared to the sample voltage traces. Also, in each pixel bin, we extracted some statistics such as mean, standard deviation, and used to train a model with that. And we can see in simulation, we tried the full data set, but experimentally, due to some limitations, it takes too long to extract the data, so we use a smaller data set of 4,000 images, but still, we can always outperform the raw binary images when trained. And this looks so a little promising. Right. You got a couple minutes. Okay. And so, just to give a summary, we have obtained controllable neuron-like responses using this NDR effect in 3-5 micropillars. We can see oscillatory bursting signals induced by both optical and electrical inputs. This only consumes, again, 230 femtojoules per burst of oscillation, and is pretty stable. For the machine learning approach, we show that using this simple scenario, the device showed great capabilities to learn, but also to generalize to unseen data. And I forgot to ask, but we also test this MNIST dataset, changing the image size, the training size, and it always outperformed the raw data training. And so for the future, we want to pass from this simple approach to a spiking neural network approach, and in order to build a full integrated system with these devices. I want to thank the team and the projects. And
let's thank our speaker.
Thank you.
One question while the next speaker sets up.
Thanks for the great talk. I've just got a question about the spiral data sets you showed. You were mentioning that noise, like the difference between simulation and experimental is noise and drift and non-ideality. How come this helps you in this case and doesn't destroy your work?
How I can tell? I'm thinking. No, because without noise kind of makes the dataset more rich, because this is just a matrix inversion. So without noise or drift, the sampling is almost the same, and noise adds a little more variation to the dataset that can help to generalize and give better results. It's more in the generalization that we can see the improvements, not so square, but in the testing we kind of have a decrease in the accuracy. Good.
Thank you.
Okay, maybe time for another question. And I know that some people have a program that say there is a coffee break now, but we have another speaker added last minute. That's you? Okay. If you can set up while somebody asks the next question. Any more questions for? Can you pass the?
Yeah. For the talk. So, do you observe under the right conditions synchronization between these fast oscillations when you couple them?
What? I didn't listen.
You have these fast oscillators, and in principle, I could imagine you observing synchronization.
We are still testing that. Yeah.